Moving not safe for work concepts from vision language models. Today we're going to be doing an in-depth review of this paper. It was written by Samuele Papi at the University of Modena and Reggio Emilia in Italy. It was published at the European Conference on Computer Vision in 2024. It has 20 citations. Your presenters are John Benjamin, myself, Asher Gibson, Zina Himes, and Adam Sachs. And our advisor is Dr. Mubarak Shah. All right, so a little warning. Some of the slides contain blurred and censored content due to inappropriate content. So we're going to go first into a little background on CLIP. So what is CLIP? CLIP is a zero-shot image classifier. This means that if we take an example like an image of a book and a possible set of captions, an open novel or book, a dog playing fetch, and a car being driven, and we pass these to the CLIP encoder. Within the CLIP encoder, it has both an image and a text encoder. These image and text encoder create embeddings for their respective inputs. These are projected into a latent space. So you can see here that the purple embedding is the image embedding, the green embedding is for an open novel or book, the yellow embedding is for a dog playing fetch, and the red embedding is for a car being driven. These are compared with cosine similarity to determine which caption matches the image best. So it is shown here that the cosine similarity for the purple and the green is the highest, so the green has the highest probability of being the best caption. So after CLIP encoder, we take a softmax of the logits to obtain those class probabilities, and then an argmax to obtain that that best class. This means that CLIP learns relationships between words and the visual representations of those words. So what's the problem with this? CLIP encoders are trained on millions of image text pairs, and within these, there are bound to be some that are unsafe, containing unsafe content. So you can see this image here, a clash between rioters and police in the evening. This is passed to a CLIP encoder, which is then used for a downstream task. And the latent representation output by the CLIP encoder is shown here. So you can see that in the latent space, we have a house, a boy, a kite, evening, sunset, and boat. But we also have the latent space polluted by riot. So based on this image here. So the result of this, when we take a harmful text query, like show me an image of a city in the evening where fighting is taking place, and we pass this to a CLIP-enabled model, such as a diffusion model, we get harmful content as output. So this harmful content is commonly referred to in the paper as not safe for work, or NSFW. So there are two primary generative tasks that CLIP encoders are used for. Text-to-image generation. So let's say we have a prompt like a burning car set on fire by gang members, and we pass this to a diffusion model, then we get an unsafe output. So that's diffusion models. And then image-to-text generation. Let's say we pass an image of 3 soldiers and one of them is injured. We pass that to a vision language model, and we obtain a text output, a seriously injured soldier laying on the ground, potentially unconscious. Both of these models use CLIP encoder, and that's kind of why they're able to generate these unsafe outputs. They learn the features from the image or text input and associate those with another image or text output. So they generate this image-text relationship feature vector that they use to associate the image and text in the latent space. So if we exchange this CLIP encoder with a safe CLIP encoder, then we will only extract the features from the inputs that are safe. So for example, a burning car set on fire by gang members, we'll only extract car. We won't extract burning or set on fire by gang members. So when it gets passed through the diffusion model, it'll output just a car. And then for the soldiers, it will see that there's 3 soldiers, 3 veterans kneeling on a beach, but it won't see that one of them is injured. So what's defined as not safe for work, or NSFW? There are 20 categories defined by the paper, and these include violence, brutality, cruelty, blood, abuse, weapons, vandalism, drug use, theft, and illegal activity, sexual content and nudity, hate, harassment, and humiliation, and suffering, harm, or suicide. These 20 categories fall within the 7 categories defined by previous literature as not safe for work. They're just more in-depth versions of those 7 categories. So the intuition behind the embedding space, semantically similar embeddings are closer together in the embedding space than not semantically related words. So if we take an image of a cat and a dog, these are going to be closer together in the embedding space because they're both pets. Whereas if we take an embedding of a table, that's going to be further away in the embedding space because it's an inanimate object. So if we apply this concept to concepts like violence, brutality, and abuse, these will be in their own space in the embedding space. And so there was some work done that shows there is a distinctive path from safe to not safe for work zones in this embedding space. So our proposed method is to fine-tune a clip encoder in order to have a latent space such as this latent space where the green area is the safe embedding space and the orange area is the unsafe embedding space. We want to design our loss functions such that the safe embedding space is more or less preserved, making sure that we don't unlearn any safe content. And we want to make sure that the latent space that is for not safe for work concepts is subject to change so that when we receive an image and or text, it will never end up in the unsafe space. Instead, if we have an example like this one, we have a dog and it's a potentially violent dog. We only want to extract dog and not violent dog. So we don't want it to end up between dog and violence in the unsafe space. Instead, we would prefer for it to just end up at dog with our safe clip encoder. So ignoring not safe for work content is our goal. So if we take a not safe for work image, v sub I star, and we pass that to a clip encoder, it's going to generate an unsafe embedding. And given that that unsafe embedding has captured both the safe and unsafe features from this image, when that gets passed to the Lava Llama LLM, or Lava Llama for causal LLM, it will output an unsafe text T sub I star. So in this image, the image shows a sink filled with red liquid, possibly blood, and a toothbrush lying in the sink. The sink appears to be dirty, and there's a cup nearby. So if we pass that same not safe for work image to the safe clip encoder, we want to generate a safe embedding such that when we pass it through the Lava Llama LLM, it will generate a safe text, only extracting the safe features from that image. So in the image, a sink is filled with water and a spoon is floating in it. There is also a toothbrush and a piece of paper nearby. So how do we achieve this goal during training? We want to take a safe image corresponding to the safe features from that image, and we want to pass that through our clip encoder to generate a safe embedding, which can be at a certain spot in the latent space, and that generates the safe text T sub I. And so when we take the unsafe version of that image, containing all the safe features plus some additional unsafe features, and we pass that through a clip encoder, we want to make sure to set that embedding space, make sure that its embedding is set to be at the same spot as the safe embedding of the safe image. So it's only extracting the safe features and not the unsafe features. So that when we pass it through the Lava Llama LLM, we only retrieve the same safe text. So in a single sentence, we take the unsafe image v sub I star and the safe image v sub I. That encodes for the same feature vector. So that's the image feature understanding vector. So we only understand the safe features and we don't understand the unsafe features. So that when that gets passed to Lava Llama LLM, it generates safe text. So we need a data set to perform this fine tuning. So we create the VSU, or Visual Safe Unsafe data set. This data set consists of quadruplets. V sub I is the safe image, T sub I is the safe text, V sub I star is the unsafe image, and T sub I star is the unsafe text. We get the first two of these from COCO. So we get the safe image and the safe text. So in this case, we have an airplane, and it's an airplane flying in a clear blue sky. And then we take our 20 not safe for work categories defined previously, and we random sample those and grab a specific category to inject into the sentence. The reason we do a specific category is because we want a balance of these 20 not safe for work categories in our data set. So we say, rephrase this sentence to include not safe for work category, safe text, and we inject the category and the safe text. The category in this case is harm. We pass this prompt to an SFT plus DPO tuned, not safe for work, Llama 2 chat 7B. That outputs an unsafe text T sub I star, an airplane crashing into a building while people are on the street. Then that gets passed to a diffusion model to create the unsafe image corresponding to these features. I am now going to pass it over to John Benjamin to continue the dataset creation and fine-tuning process details.
All right, thanks, Asha. Okay, so we're in the process of generating quadruples of safe and unsafe text and images. So creating the synthetic part of the unsafe text. So we have curated or basically crafted our own pairs of text inputs and unsafe text. So we created those on our own, 100 pairs. And we fine-tuned the Llama 2 chat with these 100 pairs to create an initial toxic text generation model. Next, to bolster that, so this process is to create, so curating 100 text samples is feasible for a research project, creating tens of thousands is not. So we're going to go ahead, take our previously fine-tuned, somewhat unsafe model and create unsafe text pairs using the clip sim and not safe for work. So we basically synthesize using our previously safe text a large amount of unsafe text samples. Next, we are going to rank these samples for pairing with the safe text so that we can find which are the most correlated in order to create the best training quadruples. Okay, so we're using the clips sim to see whether they're related on the clip image itself and using a not safe for work rate system. And then the DPO preferences creates a ranking based on those. And we fine tune the model again with the larger set of unsafe text samples for a super mean fine-tuned Llama 2 chat. With this fine-tuned chat, we are taking the COCO image pair datas, generating unsafe text from what is essentially a benign or safe image. And then we have a new Reality XL global not safe for work. This is from another work, is a fine-tuned Stable Diffusion XL model that is created specifically for generating NSFW images. And we create the image pair to go along with the unsafe text. So now that we have our VSU synthetic data set with the text and image quadruples, we are going to fine-tune using this reader loss. So we have two basic components of the loss. First is redirection. So the safe inquiries on text, we're going to redirect away from the unsafe Latin space. And the second component of our fine-tuning is preservation, which is we want to preserve the part of the Latin space that, again, is safe. So we have 4 parts of our overall, two parts of the loss function related to preservation, 2 parts related to redirection, and then we sum all 4. Why is it not going? Okay. Okay. So in this notation, the V0 and T0 are the basic clip and visual encoders, and the V and T without any subscript are the trained safe clip encoders. Again, we're trying to model, change the image production to take the image embedding away from the unsafe space and preserve everything else. Okay. So this is the redirection part 1. So unsafe text should map to the safe embedding of its corresponding image, making sure that cross-modal retrieval, as if there is no unsafe text or image related, is the same. So V0 equals V in the regular space. This is an contrastive loss. It's open LME. Okay. The second redirection loss component is that unsafe images or text inputs are adjusted so that their embeddings fall into the same space. The first preservation loss component, safe images or text are forced to retain the same embeddings as the original clip model. And finally, the preservation 2 is that safe inputs maintain the correct cross-modal relationships, matching with other safe modalities. So you can see that all 4 of these are losses are summed together on the base clip model, trained with the VISU data set, using these hyperparameters with the results. Okay, so the data set is I2P, text quality model. So as you can see, the not safe for work amount of text present is far greater, so that we have, we've shown that our synthetic data is in fact a lot worse, and so we can do higher quality redirection and as redirection of images away from that embedding space. So this is against two other text data sets. The qualitative test of text image and image to text retrieval. So this is the image quality. As you can see, SafeClip performs at the same level of these cross-modal generations without any major degradation of performance, as if there weren't any fine-tuning away from a particular part of the embedding space. And finally, it performs the unsafe to safe text to image as you would expect. So the unsafe components of the image retrieval are removed, and benign images, safe for work, are retrieved in lieu of the violent or other toxic related images. And so one of these images is censored because we decided it was not even appropriate for class. You can find it in the paper. Okay. Testing unsafe. So as you can see, the attempting to query for unsafe images using unsafe text does not succeed as well. So there's a significant degradation in terms of the ability to create a not safe for work image retrieval from a text, as well. Taking a not safe for work image is going to create a benign text. So you can see that the performance here is measured against 2. Okay, so in the diffusion case, where CLIP is used as a backbone for diffusion image generation, as you can see across the board, our safe CLIP creates a decreased level of toxic components across the board, so that our fine-tuning generally has worked. However, it has not completely eliminated the toxic components of the diffusion image generation. So you can see here are some examples. These text inputs, you do not, in a work environment, want to create or see this image. So in our safe CLIP examples, those have been removed in lieu of benign images. Okay, image to text generation. So this is the opposite of using diffusion. So this cross modality, we're using a toxic image of some sort and trying to have a text description accurately describing. Instead, we want a benign text description that does not describe the toxic trait. As you can see, SafeClip has removed to some extent those toxic elements from the text. However, you can still manipulate the embedding space to create images that seem to have the toxic components, and this is why you see our toxic components have not been completely removed in those metrics. So, in conclusion, SafeClip is an approach like others to manipulate the embedding space for a clip-like model to reduce its sensitivity to unsafe concepts. It uses fine-tuning to redirect, essentially, certain queries within the latent embedded space. And it's demonstrated through a lot of experiments that it works pretty well. And it shows that it can enhance the safety and trustworthiness of an image-to-text model. Okay, and then you can access the synthetic data set, but you need to request permission. All right, any questions?